Good evening. I'm not done grading your test yet. I'm sorry. I'm still working on it. Give me until Wednesday. I hope I'm done with Wednesday. On Wednesday, we are done. Okay. You can minus me 1 point right now. I minus you another 1 point later. No, I'm no, I'm kidding. No, trust me, I will be nicer because of this. Okay, let me start. Again, I assume you already watched the lecture video corresponding to that 11.2. I will summarize what you really need to know from this section. 11.2 on series. What is a series definition? Let A sub n be a sequence. In this case, it is an infinite sequence. Then Sn is the nth partial sum of that sequence, which is defined to be the sum from from I equals 1, from I equals 1 up to the nth term of A sub I. So when we say nth partial sum, it refers to the sum from the first term up to the nth term. Okay, that's the sum of the first n terms. Now, the sequence Sn, so you see you have n partial sum, right? Now that n partial sum form a sequence. Okay, that n partial sum form a sequence is convergent if Sn, the n partial sum converges to S. Okay, and if so, then the infinite sum of A sub n, that's basically, to be more precise, A sub I from I equals to 1 to infinity, okay, is equals to S. Now think of this in the following sense. Remember when we integrate integral from some number, let's say 1 to infinity of fx dx, we say that this integral is convergent if the limit t goes to infinity of the definite integral 1 to t fx dx is convergent. Okay, so basically the infinite sum that we are dealing with here is being computed by taking the limit of the upper term. Okay, that's the illustration. Okay, now this S here is the sum of the series which refer to infinite series. Okay, that's the first one. So the way we compute, the way we see if the infinite sum is convergent or not is by looking at the partial sum. Okay, we try to find the general formula for the partial sum and then bring the n to infinity. Okay, that's the first things that we need to know. Second, geometric series. Let's start with geometric terms, geometric sequence. Geometric sequence has the form a sub n equals to a sub 1 times r to the n minus 1. Remember in the last lecture, in the last discussion, I said that it mimics exponential function. Y equals to a b to the x minus 1. Okay, now geometric series is the n partial sum, that's the sum from 1 to the n term of a sub 1 r to the I minus 1. Okay, the r here is the common ratio. And this is equal to the first term times 1 minus r to the n over 1 minus r. Okay, that's the geometric series. Now, the geometric series and the n partial sum. If the r has magnitude less than 1, then you will see that r to the n will converge to 0. Let's say you take r equals to 0.5, 1/2, right? So r to the infinity will be very, very small, right? You can imagine base 1/2, exponential function base 1/2, right? Now, what I want to emphasize is that because if the magnitude is less than 1, then r to the n will converge to 0, and therefore the Sn, the n partial sum, will converge to the infinite sum of geometric series, which is given by a sub 1, the first term, over 1 minus r. Notice that in this formula, this is the one will go to 0. Okay. Now let me do the proof for this one formulas. The reason I want to go over the proof for this formula is because it is actually using something called telescoping method. Okay, it used something called telescoping method. Implicitly, proof. See, S sub n, the sum of n partial sum of geometric sequence will be, the first term is a sub 1, the second term is a sub 1r plus a sub 1r squared all the way to a sub 1r to the n minus 1. That's the sum of the nth partial sum. The sum of the first n partial terms. Now, if I multiply by r both sides, notice that a sub 1 multiplied by r becomes a sub 1 times r. So this guy, when you multiply by r, will give you that, right? Now, if you multiply this term by r, it becomes a sub 1 r squared. And keep on going until, for the previous term here, it becomes a sub 1 r to the n minus 1. And this term here, if you multiply by r, it becomes a sub 1 r to the n. Now, what we mean by telescoping is that when you add, or in this case, when you subtract, these terms in the middle will cancel. You see that? These terms in the middle will cancel. So I have S sub n minus r times S sub n equals to a sub 1 minus a sub 1 r to the n. Okay, you see what happened is when you telescope that, okay, the middle terms cancel. Now on the left-hand side, you factor S sub n. On the right-hand side, you factor a sub 1. So the nth partial sum will be the first term times 1 minus r to the n over 1 minus r. That's the end of the proof. Okay, that's the end of the proof. Now, of course, if you want to continue the second part of that proof, then we say that for magnitude of r less than 1, r to the n converges to 0, such that S infinity will be a sub 1 times 1 minus 0 over 1 minus r, right? So the infinite sum will be the first term over 1 minus the ratio. But this is only true if the magnitude of the common ratio is less than 1. Okay, there's another one technique called telescoping method, telescoping sum. We will do this later in example. Okay, and then the fourth thing you need to keep in mind is that if the infinite sum is convergent, then maybe I use this notation better. If the infinite sum is convergent, then a sub n converges to 0. The sequence converges to 0. if the series is convergent, then the sequence must converge to 0. Okay, but the converge is not true. But the converse is not true. Simply because the sequence converges to 0, it does not imply the series must be convergent. No, that's not true. Okay, and the counterexample is harmonic series. Harmonic series is the series, the infinite sum of 1 over n. Notice that 1 over n converges to 0, but the sum is infinity. Okay, you can see the explanation in example 4 in our textbook. I'm sorry, example 8 in our textbook. Now, this series is so well known such that we give it a special name, harmonic series. We use that a lot as a counterexample, even in future. Okay, but because of this note number 4, then we know one thing. Suppose the sequence is not convergent to 0, it implies the series is divergent. Now we call this contraposition. Okay, we call this contraposition. See, if not this, then not this. Okay, that's for, we call this test for divergence. That's the first test of divergence actually here. How do we know that a series is divergence? Look at the last term, the infinite term. If it is not 0, then it's divergent. Okay, the sequence may be convergent, but as long as it is convergent to something not 0, then the series is divergent. Okay. Last one, some theorem. This theorem actually coming from integral, very similar to integral. And limit theorem. If series A and series B are convergent, then the series of constant multiple of A sub n that is equal to constant multiple of the series. The series of the sum and the difference of those two sequences is equal to the series of the first series plus or minus the second series. Okay, but only if each series, each component is divergent. Okay, that's basically the summary, what we need from this section. Okay, first we will learn about notation. Each series needs to be convergent or divergent. For the last theorem, it has to be convergent for this to apply. Okay, it has to be convergent. Let's see number 15 first. Okay, let the sequence a sub n be 2n over 3n plus 1. Part A is thus, I think should I say the is, not thus, is the sequence a sub n convergent as a sequence. Solution. We're talking about the sequence, right? So apply the limit 2n over 3n plus 1. What happened when n goes to infinity? This is equal to 2 over 3 plus 1 over n, which converges to 2 over 3 plus 0, which is 2 over 3. So the sequence is convergent. But how about the series? Is the sum of this series from 1 to infinity convergent? Solution, the answer is, you see that a sub n converges to 2/3, which is not 0. So the series, even though the sequence convergent, the series is not. It's divergent instead. Thomas, I can't really tell which one is which one. Now you see, let's do it a bit slower for this question here. I do it slower. Okay, let's see. The first term is 2 over 3 plus 1, right? The second term is 4 over 6 plus 1. The third term is 6 over 9 plus 1, so on and so forth. So the sequence basically going 2 over 4, 4 over 7, 6 over 10, 8 over 13, and of course it gets larger and larger, and the numerator gets larger, the denominator gets larger. But eventually, the sequence approach very, very close to 2/3, right? As you go very far, as n goes really big, it becomes very, very close to 2/3. Now, imagine if you add these numbers though, then that will be 2 over 4 plus 4 over 7 plus 6 over 10 plus 8 over 13 You keep on adding, and eventually you will adding a positive number. You keep on adding positive numbers. You see that? So it will not be convergent because as long as you add something non-zero, then the value will keep on changing, right? That's why if the sequence is not converging to zero, let's say it converges to 2/3 instead, then your series, after you go very far and pretty big, then you will basically keep on adding that terms. But if you keep on adding non-zero terms, then of course it will not, the series will not be convergent. Okay. But Thomas, what happens if we keep on adding zero? Even that may not be good enough. Okay. Why? Harmonic series. Harmonic series. It turns out that even though the sequence goes to zero, it goes to zero way too slow, such that the area or the terms still add up to infinity. If you remember the graph of 1 over n, if you take the area from 1 to infinity, right, you see the sequence goes down to 0, right? The sequence goes down to 0. Okay, but if you compute the area under this 1 over integral from 1 to infinity of 1 over x dx, this is divergent. So even though the function dies down to 0, but the area under the curve still explodes to infinity. In other words, it dies down to 0 too slow, such that the area still explodes to infinity. Okay, that's for number 15. Number 17. I tried to do more problems here because this 11.2 is actually a big foundation for what we will have in future. So number 17, you have this series, 3 minus 4 plus 16 over 3 minus 64 over 9, so on and so forth. They tell us this is geometric series. That's nice. The first term is 3, right? This is the first term. What is the common ratio? The common ratio is the next term over the current term. Or you can also use the third term divided by the second term, or the fourth term divided by the third term. Okay, you will get -4 over 3, right? But notice that absolute of the common ratio is 4 over 3, which is greater than 1. Okay, so the geometric series, can you tell what is the geometric series, by the way? This is the infinite sum from n equals to 1 to infinity. The first term is 3, the common ratio -4/3 to the power of n minus 1, right? Remember, the first term times r to the n minus 1. So this geometric series is divergent. Okay, actually all you need to do is to look at the common ratio. All you need to do is look at the common ratio. If the common ratio is has magnitude less than 1, then it will be convergent. If the common ratio is greater than 1, the magnitude is greater than 1, then it will be divergent. Let's see number 21. We have the series, the infinite series from n equals to 1 to infinity of 6 times 0.9 to the n minus 1. Solution. We don't even care about the first term. Do you realize that? We just look at the common ratio 0.9. The magnitude, therefore, is less than 1. So the geometric series is convergent. Okay, we can go even further. If it is convergent, then convergent to what? Convergent to the infinite sum equals to the first term, which is 6 over. How do you know what is the first term? You set n equals to 1. Okay, you set n equals to 1. So a sub 1 will be 6 times 0.9 to the power of 1 minus 1, right? That's how we get that 6. Okay, so the infinite sum will be the first term over 1 minus the common ratio. Infinite sum will be 1 over 0.1, that's equals to 60. Okay, so basically we are saying that this infinite sum from the first to the infinite term of 6 times 0.9 to the n minus 1 is equals to 60. That's for number 21. Now, how about number 23? Infinite series from 1 to infinity of -3 to the n minus 1 over 4 to the n. Now, this is not in geometric series pattern, but we can make it geometric series pattern. Let's play a little bit. This is equals to the infinite sum of -3 to the n minus 1 over 4 times 4 to the n minus 1. Can you see that? I basically break this part here, becomes this. Right? Now what I will do next is, I want to have exponent n minus 1. So later on, I will combine these two. Okay? I will combine those two later on. So this is equal to the infinite sum from 1 to infinity of 1/4, -3/4 to the n minus 1. Right? So you see that the first term is 1/4. The common ratio is -3/4. Right? Now, because the common ratio has magnitude 3/4, which is less than 1, so the series is convergent. In fact, we know it is equal to the first term on the top over 1 minus the common ratio. Okay, so that's 1 over 4 divided by, the bottom will be 7 over 4. That's 1 over 7. Okay, so the series is convergent to 1/7. Now, the key part from this number 23 is that you basically need to massage the sequence inside the summation to fit into the pattern of coefficient times common ratio to the n minus 1. Okay. Number 25. Let me do it here. Infinite sum of n from 0, not from 1, to infinity of pi n over 3 to the n plus 1. Let me massage it this way. Suppose I start from 1 instead. So I change the counter. Instead of starting from 0, I start from 1. So this guy here, the pi, must be to the n minus 1, right? You see, the first term is when n equals to 0, right? So when n equals to 1, then this will be 0. And the denominator here will be 3 to the n. Just imagine, if I write this out, this will be, if I write the numerator out, that will be pi to the 0 over 3 plus 3 to the 1, right? Pi to the 1 over 3 squared. Pi squared over 3 cubed, and on. Are we going over material for test or new material? I will do it in my office hour on Saturday to go over all tests. If you take a look on the schedule that I mentioned last time, give me a second. Yeah. Notice that I will not go for any old tests. Okay, I will do on Saturday office hour, I'll review for test 3. Okay, but not today. Okay, today we do 11.2. At what time? During my office hour on Saturday. Pay attention to detail. Saturday office hour. Okay, that's why I say in my discussion there, my office hour. Okay, so Saturday on May the 1st, office hour from 8 to 10. Now, the reason I do it there on Saturday, because I need to be there anyway, but usually nobody's coming. So what I will do is I basically record me going over the test 3 and some problems from all test 3. Okay, if any students there, you can ask me a question. If not, it's still recorded anyway. Right? Then I post the recording for you. Okay, that's my plan. That's my plan. Okay, why don't you do that last Saturday, Thomas? Because last Saturday, I need to give makeup tests. 2 Saturdays ago, I still need to give makeup tests. So you see that 2 out of 3 Saturdays, I actually give makeup tests. Yeah, 2 out of 3 Saturdays, I do give makeup tests. Well, anyway, okay. This way, then we can advance as much as possible. And no, our class time not supposed to go over all tests, though. That's not a wise way to spend our time. Well, anyway, I rather use my office hour for that. Okay, now if you extend these terms, you see you have this, right? Now try to adjust this such that the counter start from 1 instead of start from 0. Okay, so you see that our first term, that's pi to the 0 over 3 to the 1, right? So you adjust the counter. If you are in computer science major, you know what I'm talking about. Okay, now then from here, you massage. Massage what, Thomas? Make it in a way such that you have only the first term times r to the 1 minus 1. That's what you want. Okay, so I will break down. I will break the 3 becomes 3 times 3 to the n minus 1. So it becomes 1/3 pi over 3 to the power of n minus 1. So you see now it looks like the summation of the first term times r to the n minus 1, right? Then from there you can read further. Read what? What is the common ratio? That's pi over 3. But that's greater than 1, Thomas. Oh, then you can summarize that right away. So this series is divergent. Okay, this series is divergent. Number 27. Determine whether the series is convergent or divergent. We have this series 1 over 3 plus 1 over 6 plus 1 over 9 plus 1 over 12 plus 1 over 15 and all the way. Can you write it in summation notation? That's 1 over 3, 6, 9, 12. Oh, that's linear on the denominator. We start from the first term to infinity of 3n. Is it right? But this is the same to 1/3, the infinite sum of 1/3 times 1 over n. According to one of the theorem we have, if you have constant multiple, you can bring it out. But we know this is, but this series here is divergent. Okay, it is a harmonic series. Then 1/3 times that harmonic series is divergent as well. Number 29. The infinite series from 1 to infinity of n minus 1 over 3n minus 1. Is it convergent or divergent? And whatever your solution is, you need to argue why it's convergent and convergent to what, If it is divergent, you need to explain why. Remember, your tools are these 6 things here. Okay, I think what I will do is always think of this one. Okay, look at the limit of that sequence. Look at the limit of that sequence. Okay, so A sub n is n minus 1 over 3n plus, minus 1, right? Which is equals to 1 minus 1 over n over 3 minus 1 over n. If you divide by n, the top and the bottom. But this will be convergent to 1 minus 0 over 3 minus 0, which is 1/3. Right? Which is not 0. So, by tests for divergent, you may even need to quote the name. That series is divergent. So if the sequence is not convergent to 0, then the series is divergent. Basically, in long run, you keep on adding 1/3, 1/3, 1/3, 1/3, like that. That's for number 29. Okay, I think I have done enough. I would like you to do some problem. Number 31. If you have this series. Is this convergent or divergent? And why? My suggestion is you break it into 2 sums. I'm sorry, it should not look like that. It should look like this. Okay, and then break it into 2 sums. Sum of something plus the sum of something. Remember, the series of sum equals sum of series, right? That's one of the theorem we have. This one here. Series of sum equals to sum of series, right? Just like we have integral of sum is equals to sum of integrals. Of course, if the series or the integral is convergent. N equals 1 to infinity of 1/3 to the n. This is 2/3 to the n. You can actually tell already that the first sum here, the first series here has r equals to 1/3, and the second series here, the r is 2/3. Both of them less than 1. Both of them has magnitude less than 1. Let me write it this way instead. Right? Okay, so this series is convergent and the other series also geometric and convergent. Can we answer convergent to what? Let's go more details then. What is the first term? When n equals to 1, it's 1/3. When n equals to 1, it's 2/3 here. Okay, so this sum is the first term over 1 minus the common ratio, which happens to be the same. Gada bum, gada boom, that's 1/2. While the second part, the second terms, the first term is 2/3. The ratio is also 2/3. Gada bum, gada boom, that's 2. Convergent to 2 plus, I'm sorry, 1/2 plus 2, which is 2.5. Number 33. The infinite sum from 1 to infinity of the nth root of 2. This will never be 0. I mean, the sequence will never be 0. Is it right? A sub n is actually 2 to the 1 over n. Do you know what it converges to? I mean, it's always positive, right? This goes to what? When n goes to infinity, this will be 2 to the 0, which is 1, right? By test for divergence, because the sequence not converging to 0, then this infinite sum of nth root of 2 is divergent. Now, your turn. I want you to do some problems. So at this point, either you make it geometric and then decide, or look at an infinite sequence. Is it convergent? At this point. Okay. So I would like you to try number 35. That's the infinite sum of natural log of n squared plus 1 over 2n squared plus 1. I can tell you the answer, but I need you to give me the argument. This is divergent. You give me the argument. That's more important. Number 37. Infinite sum from 0 to infinity of pi over 3 to the k. Oh, actually, this is from k equals to 0, not from n equals 0. Also, number 39. You can do that. Is it convergent or divergent? Okay, number 41, I will do it later. But let me ask you to do this first, especially the argument, okay? This chapter 11 is difficult for a lot of people because they don't know how to argue. And usually you don't know how to argue because you don't get used to show your work. Now you really have to show your work. Okay? Right now is 8:16, 1, 2, 3, I think 3 minutes each. Actually 2 minutes each is good. I will come back at 8:25. Okay, try it first. Okay, so for example, remember I give you this hint for now. Either you make it geometric or look at the final term, the sequence. Okay, now, number 35, for example, it's definitely not geometric, right? It's definitely not geometric. So take a look on the last term. That's equals to natural log of 1 plus 1 over n squared over 2 plus 1 over n squared. But this converges to natural log of 1 plus 0 over 2 plus 0. Right? Which is not 0. Agree? Okay, now but you need to give argument by test for divergence. Then the series is oh, by the way, one more thing. When you summarize, you need to quote the series again. Don't just say, oh, by test of divergence, the series is divergence. No, you need to write down this series explicitly instead of saying the series is divergent. No, don't do it this way. Okay, be explicit on which series you're talking about, because in later terms, in later sections, we will use another series to prove that this series is convergent or divergent. Okay, so I want you to be explicit, and notice that I have that since the very beginning. I don't just say, oh, the series is convergent, the series is divergent. No, I have been explicit. Now, number 37. Does it look like geometric series? You can tell it's geometric series if you have some base, a constant base, to counting to some power. Okay. Now from there, you see, oh, then what is the base? What is the common ratio? The common ratio is pi over 3, but this is greater than 1 though. Right? So this series is divergent. So what happened in this case, I look at that as a geometric series, and the common ratio has magnitude more than 1, so the series is divergent. How about number 39? Whether it starts from 0 or 1 doesn't matter? No, it doesn't matter. It doesn't matter. It doesn't matter if it starts from 1 or from 0 or from any other number, because what makes it convergent, divergent, not the first couple of terms, right? Okay. See, when k is 0, like in this case, let me use different color. When k is 0, and instead if you start from 1, if you start from 1 and it is convergent, adding some number will still be convergent. But if this guy here is divergent, then adding this constant will not change it to convergent, no. In other words, what determines if it is convergent, divergent is not the first couple of terms. Okay, very good question, however. Very good question. So the first couple terms does not tell us if the series will be divergent or divergent or convergent. Okay, how about this one here? The nth term, tangent inverse of n, this will converge to what? Anybody? That's the key though. That converges to pi over 2, right? Which is not 0. So by test for divergence, this series is is divergent. Now, instead of doing number 41, I really want to do number 41. I really want to do number 41, but I guess I cannot yet. Because that one requires me to use telescoping. Let me do number 43 first. Number 43, the infinite sum from n equals to 2 to infinity, so it doesn't start from 1, of 2 over n squared minus 1. Usually we use telescoping method if the sequence looks like we can apply partial fraction decomposition. So look at A sub n. So this A sub n is equal to, I think it will be 1 over n minus 1 minus 1 over n plus 1. How do you get that, Thomas? Guessing. I did it by guessing, but here's the thing. We will do partial fraction decomposition, okay? 2 over n plus 1, n minus 1 will be something over n plus 1 plus something over n minus 1. Multiply both sides by the LCD. And set n equals to 1, I will get 2 equals to 2b. So the b is 1. When n equals to negative 1, it'll be negative 2a. So a is negative 1. So 2 over n plus 1, n minus 1 will be negative 1 over n plus 1 plus 1 over n minus 1. Okay, which is this guy here. In other words, now we can see the following. Okay, summation from n equals to 2 to I of a sub n will be, when n equals to 2, it will be 1 over 2 minus 1 minus 1 over 2 plus 1. That's when n equals to 2. I need more space. Let me bring it down a bit. Plus when n equals to 3. That's when n equals to 3. Plus when n equals to 4. How far do I need to go, Thomas? Until you fill the pattern. And keep on going, keep on going. Okay, until I. So this will be 1 over I minus 1 minus 1 over I plus 1. That's the ith term. This is equal to 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5, so on and so forth. But you see that this guy here cancels this. You see that? Okay, and later on, this 1/4 here cancels the 1/4 we have here. Right? If you want, you can do more terms so that we can see it better. Let's do more terms so that we can see it better. This is 1/4 minus 1/6 plus 1/5 minus 1/7. So you see when I do canceling, oops. When I do canceling, I always have two terms left at the front. 1 plus 1/2 will not be canceled, right? Okay. But up to n equals to 6, n equals to 2, 3, 4, 5, 6. Up to n equals to 6, I get the last two terms not canceled. Do you see that? In other words, if I continue further, I will get 1 over I minus 2 minus 1 over I, and then plus I minus 1 over 1 over y plus 1. This will get cancelled, right? Cancelled. This will get cancelled. This will get cancelled. I have the last two terms left. In other words, this is 1 plus 1/2 minus 1 over I minus 1 over I plus 1. That's the sum up to I. Now you send it to infinity. Limit I goes to infinity of this. That will be just 1 plus 1/2, which is 1.5. Now then summarize. So the series n equals to 2 to infinity of 2 over n squared minus 1 is equal to 1.5. Now what we mean by telescoping is after you write the terms out, okay, some middle terms cancel and you are left with only some terms at the beginning and some terms at the end. At which, when I goes to infinity, the blue parts disappear. Okay, now that's what we mean by telescoping. Let's try again. Number 43. The sum, infinite sum from 1 to infinity of 3 over n times n plus 3. I hope you have that instinct that this is actually the same to 1 over n minus 1 over n plus 3. Is it right? Which number was the last problem? Number 41. Last one is number 41. That's number 43. So this should be number 45. Thank you. Yeah, this is number 45. Thank you. Yeah, this one is clear. It's 3. The difference of the denominator is 3, right? Okay, so you see this will be n plus 3 on the top minus n. Is it right? Okay, basically from, wait a second. Basically from here to here, you do partial fraction decomposition. Okay, now assuming you are done with the partial fraction decomposition, then you will do the following. the summation from I equals to 1 to only n. That's equals to the summation from I equals to 1 to n of 1 over I minus 1 over I plus 3. Which, if I list them out, that will be 1 over 1 minus 1 over 4 plus, that's when n equals 1, when I equals 1, when I equals 2, when I equals 3, when I equals 4. I equals to 5, I equals to 6. Of course, you don't want to make it too long, right? Okay, so up to actually this will be n. Now let's start doing the canceling from the beginning. So 1 over 4 will cancel this. 1 over 5 will cancel this. 1 over 6 will cancel this. Okay, so if I have 1 over 7, notice that I always have these 3 terms at the beginning, never get canceled. And the last 3 terms will not get canceled. Do you notice that? Okay. In other words, in long run, this will get canceled, but not the last 3 terms, this guy. This guy will not get canceled. So that is equal to one plus 1/2 plus 1/3 minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. Okay, that's the nth partial sum of 3 over I plus 3. Now then I bring to infinity, n goes to infinity. So the purpose we do the partial sum is so that we can get the pattern. Then we know what to cancel. Now then from here, so so the infinite sum from 1 to infinity of 3 over n times n plus 3 is equal to 1 and 5 over 6. Or you can also say 11 over 6. Now let me go back to number 41. Infinite sum of 1 over e to the n plus 1 over n times n plus 1. N equals to 1 to infinity of these terms is equal to, now make sure that both of the ones, if you separate them, make sure that they are both convergent though. Okay, it is not true if any one of them not convergent. Okay, series of sum equals to sum of series, but only if both of them convergent. So I need to show that both of these series actually convergent. Okay, let me work it out one by one. Now, every time you want to do detachment, you always need to start all over. Don't use equal sign, no. You do detachment for the series n equals to 1 to infinity of 1 over e to the n. The first term is 1 over e, right? Okay, the first term is 1 over e. How about the common ratio? The common ratio is also 1 over e. You can modify it this way if you want, so that you can see it better. That's 1 over e times 1 over e to the n minus 1, right? Okay. So the infinite sum is the first term over 1 minus the common ratio. Multiply the top and the bottom by e, I get 1 over e minus 1. Now this is not equal sign, this is a column. Basically, I want to say that this is geometric. Oops. The first term is 1 over e, the common ratio also 1 over e. Now how about the second series? For the series n equals to 1 to infinity of 1 over n times n plus 1. This is the infinite series of, if you can do it fast, that would be great, 1 over n minus 1 over n plus 1. Right? This is the limit of I goes to infinity of 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 all the way to the i's term, 1 over I minus 1 over I plus 1, where the I goes to infinity. And then you see that this guy cancels, this guy cancels. So something always cancel, like even in the, after you have 3 terms, only 1 term at the beginning not being canceled and only 1 term at the end not being canceled. Right? In other words, if I go far enough up to I term, even 1 over I will get canceled. This is equals to limit I goes to infinity of 1 minus 1 over I plus 1. But this is equals to just 1. Okay. So the series n equals to 1 to infinity of 1 over e to the n plus 1 over n times n plus 1. This is equal to 1 over e minus 1 plus 1. It's e over e minus 1. Okay, now that's for that telescoping and geometric. Number 51. Express the number as ratio of integers, 0.8 bar. Express this as a ratio of integers. Remember somewhere in the past, long time ago, long time ago, long time ago, we say that repeating decimal is rational. Which means we can express this repeating decimal as the ratio of two integers. Okay, how do we do that? I will show you the first method called textbook method. This is what they want you to do. That's 0.8 bar is equals to 0.8 plus 0.08 plus 0.008, so on and so forth. Right? Which is basically equal to 8 times 1 over 10 plus 8 times 1 over 10 squared plus 8 times 1 over 10 cubed. Is it right? But that is a geometric series. That's a geometric series with the first term is 8 over 10. Maybe I write it this way first. This is 1 over 10 to the n, right? So the first term is 0.8. The common ratio is 1 over 10. Do you see that? When n equals to 1, that's 0.8, right? But as n increases, the exponent here increase. So that's how we know that's the ratio. Okay, so this is equal to the first term over 1 minus the common ratio. Multiply the top and the bottom by 10. That will give me 8 over 10 minus 1. That's 8 over 9. Okay, you can use your calculator. 8 over 9 is equal to what? That's textbook method. By the way, that's textbook method. Basically, textbook methods try to rewrite that as geometric series whose ratio is less than 1. Okay, Now, telescoping method. I don't want to call this Thomas method, even though it starts with T. Let's say the sum S is 0.88888 forever, right? Now notice that it repeats every one digit. It repeats every one digit. So if I multiply by 10, it will move by one digit. Do you see that? Now subtract that. You will get negative 9s equals to negative 8. So the sum that we get earlier, which is 0.8888 something, becomes 8 over 9. That's it. End of story. Mickey Mouse. Number 55. After this, I will take a break. Number 55, express this 1.5342 bar as the ratio of two integers, the ratio of integers. Let's call that x. Notice that it repeats every two decimals. So if I multiply by 100, the decimal point will move by 2. Let me move this a little bit to the right so that I can have a better visual for the next line. So if I multiply by 100, I will get 153.42424242 and on, right? I move the decimal point twice to the right. Now then I will subtract this. I will get negative 99x is equal to, I subtract backward, that will be negative 98110. Let me use my calculator to make sure. I know this part will cancel. This part here will cancel, right? So what I need is 1.53 minus 153.42. So my x is equal to 151.89 over 99. But the top one is not integer. How to make it integer? Just move the decimal point twice to the right on the top, and also move it twice to the right at the bottom. And I think both of them multiple of 3, right? Yeah, both of them multiple of 3. So if I reduce by 3, at this point we are actually okay. It's already integer over integer, right? So we are actually done here. They just want us to make it integer over integer. They don't tell us to make it to simplify the fraction, right? But if you want, you reduce by 3. And then you can use your calculator. 5063 divided by 3300. It will give you what we want. Okay, let me take a break. Right now it's 9:04. Let me come back at 9:15. We'll do next number 57 and on. Number 57, find the values of x for which, maybe I say it such that the series in this case of -5 to the n x to the n is convergent. Now the idea is, in this case, you rewrite that series as a geometric series, and then you set the ratio to have magnitude less than 1. Okay, so what I will do is I will rewrite that series this series is equal to the series, infinite series for -5x to the n. Is it right? Okay, which we can write that as -5x times -5x to the n minus 1. Just for sake of completeness, that we can see the first term, this is the first term, and this is the common ratio. You see that? Okay, which you can see the common ratio already start from there. And remember that a geometric series is convergent if and only if the common ratio has magnitude less than 1. So the magnitude of R, which is -5x, should be less than 1, right? Absolute of -5 is 5. So absolute of x should be less than 1/5. So x has to be between -1/5 to 1/5. And it has nothing to do with the first term. Okay, it has nothing to do with the first term to make it convergent. Okay, so the series and from 1 to infinity, -5 to the n, x to the n is convergent to -5x over 1 minus -5x when x is between -1/5 to 1/5. And that's it, we are done. Number 50, maybe number 61. Oh, 59 first, number 59. Find x such that the series is convergent. decomposition, you see that that series can be rewritten as x minus 2 over 3 to the n, right? Okay, which is convergent, is geometric, with r equals to x minus 2 over 3. Okay, so the absolute of that common ratio will be less than 1 if absolute of x minus 2 is less than 3. Is it right? You multiply both sides by 3. So x minus 2 is between -3 and 3. So x is between -1 to 5. With r equals to, I'm too fast, r equals to x minus 2 over 3. Convergent if we have that, right? Now, what is the first term, by the way? The zero term in this case. The zero term is when n equals to 0, right? That's 1. Okay, except when x equals to 2. Okay, so the infinite sum will be equal to, the first term is 1 over 1 minus the common ratio x minus 2 over 3. For x not equals to 2. Can you tell what is the sum if x equals to 2? When x equals to 2, x minus 2 will be 0, right? We are basically adding 0 plus 0 plus 0 plus 0 plus 0 plus 0, right? Okay, so the infinite sum for x equals to 2, that's 0. Let me go on further. So this will be multiply the top and the bottom by 3. I get 3 over 5 minus x for x not equals to 2. Okay, I'm basically done with this section. Now let's do some harder part. I think the later part here, more into conceptual. So let me pull a line. The following problems are conceptual. And it will be helpful if we know some concepts behind this sequence series thingy. For example, number 67. I think I have never gone over problems past number 63 in this section. In my old lectures, right? I never really go over this. So it says the following in number 67. So we have infinite series. Okay, that's the infinite series, which nth partial sum, whose nth partial sum, whose nth partial sum is equals to n minus 1 over n plus 1. The question is find a sub n and the infinite sum. So if you have the nth partial sum formula, can you find the infinite sum? I think the second question is easier. The second question is easier. So solution, let me do the second part first. Okay. This guy here, the infinite sum, is basically equals to limit n goes to maybe I to infinity of the ith partial sum. Is it right? Which is equal to limit I goes to infinity of the nth partial sum, the ith partial sum. That is limit I goes to infinity of I minus 1 over I plus 1. Divide by I on the top and at the bottom. That will give me 1. The first question requires some understanding. Let's take a look on S1. So this is something else, okay? Something else before I go back. Notice that S1, the first partial sum is basically the same to the first term. S2 equals to A sub 1 plus A sub 2. S3 equals to A sub 1 plus A sub 2 plus A sub 3. Which I can say this is equals to S2 plus A2. I'm sorry, A3, not A2. Okay. S sub 4 will be the sum up to the third term plus the fourth term, right? Okay, such that you see in general, S sub n is equals to S sub n minus 1, the previous sum plus the current term. So if we go, so we can say that the current term is actually the nth partial sum minus the previous partial sum. Now that's what we will use for A sub n. A sub n equals to the nth partial sum minus the n minus first partial sum. N partial sum will be n minus 1 over n plus 1 minus the n minus first partial sum will be n minus 1 minus 1 over n minus 1 plus 1. That is n minus 1 over n plus 1 minus n minus 2 over n. do the LCD, n times n plus 1 on the denominator. On the top left, n times n minus 1 minus n plus 1 times n minus 2. That is n squared plus minus n minus n squared minus n minus 2 over n times n plus 1. Gada-bum, gada-boom, that's 2 over n times n plus 1. Number 82, maybe number 80 first. Wow, I really hardly go this far, but I try to show you how to do proofing in much higher level in math later on. If you are in electrical engineering or in computer science, then and physics and other things, of course, not only this, you need to be stronger in proofing. Okay, now number 80. Suppose the infinite series of A sub n is convergent. A sub n, the term is not equals to 0. So you are not doing 0 plus 0 plus 0 plus 0 plus 0. They show that the series of the reciprocal is divergent. Proof. What do we know if a series is convergent? One of the things we know is that limit of the sequence is 0. Is that right? Okay, and therefore, limit n goes to infinity of 1 over a sub n will be infinity. Okay, or to be more precise, undefined. Plus or minus infinity, I should say, which is not 0. Now that implies the series itself by divergence, test for divergence, and the infinite sum of 1 over a sub n is divergence. Okay, so the argument is actually quite short, but by doing proofing, you see more the reason why something works that way. Intuitively, you know, oh yeah, it will be divergent, but why? I feel that it is divergent. No, never use feeling to prove something. Okay, never use feeling to prove anything. Feeling does not prove anything. It may be a good guide, okay, but you never judge anybody by feeling. Okay, That's actually a very big warning, not only in math, though, even in real life. Number 82. Yeah, turned out to be deep, huh? When I was in middle school, my friend gave me a t-shirt. A t-shirt. Do you know Fido Dido? Anybody ever heard this Fido Dido? Do I have any way to show that? I wonder if, let's see if it's online. Fido Dido is a character that is very close to my friend. He's a very good friend of mine until now. Fido Dido. This character here, this guy. Okay, so if you ever see me in person, you will notice that my haircut is basically like this. So I like my haircut to be short such that my hair becomes spiky, at least when I was in middle school. Okay, that's the character. Now, the thing is, I wonder if they actually have it here. Feeling is not. Does it have it? Give me a second. I kept that, you know, I wore that shirt until it's just so bad, so bad. I start when I was in middle school until I was around, like at least like around 15 years after that. I wore it until it's just, you can't even use that even as just to wipe anything anymore. It's just a lot of holes. No, it doesn't have it, huh? How about feeling is? Still no? I wish I have that picture though. Well, anyway, basically it says that feeling is a dangerous guide. I really thought it's somewhere. This is a very, very old character. Think of that as something I already have like around 30 years ago. I'm 40 something right now. And I get it when I was like around 14 years old. Yeah, around 30 years ago. Fido Dido feeling is. Do they have it here? Well, anyway, let's go back to our discussion. So it basically have that character, easy to sketch. Feeling is a dangerous guide. Notice that it doesn't say it's wrong. Okay, it's just that sometimes our feeling over summarize the mathematical pattern such that we are not aware with some fallacies. Okay, now notice in number 82, if the infinite series is divergent, and C is not equals to 0, show that the infinite series of C A sub n is also divergent. Notice we cannot use this one. We cannot say that if this series is convergent, then this is convergent. You can't, because this theorem here starts with a convergent series, not with divergent series. How do we prove that? In other words, we cannot do this. We cannot do the following. Okay, you cannot say that sum of C A sub n is equals to C sum of A sub n, therefore that's divergent. No, you cannot say it that way. You cannot say it that way. This is not true. At least for now. At least for now, this is not true. We don't have that proof yet. That's not one of the theorem. What we have is when it is convergent, if this is convergent, then multiplied by C will still be convergent and equals to this. But it may not hold if the original series is divergent. So how do we prove this? I can come up to two different ways to prove this, I think. But I like the contraposition argument. Contraposition argument. This is also known as proof by contradiction. Okay, in which we start from the conclusion, what if the conclusion is not divergent? Okay, so suppose the sum of C A sub n is not divergent. Well, it means this series is convergent, right? But we start from the hypothesis that it is not divergent. Okay, so we start from the negation of this. Now, suppose this series is convergent. Now, since C is not zero, then 1 over C is not infinity. It is a real number, right? It is a real number. By the theorem, that if we have a series that is convergent, then 1 over C times that series, which is equal to the infinite series 1 over C times A sub n, which is the series of A sub n, is also convergent according to that theorem. But that's a contradiction. Contradiction to what? we say that the original series is divergent, right? That's contradiction to what we had here. In other words, contradiction to the series is divergent. In other words, you cannot have the infinite series C times A sub n, which is convergent, at the same time the original series is divergent. You cannot have that at the same time. Now, this is what we mean by proof by contradiction. Okay, so you assume first, you suppose first that the conclusion is not true. Your conclusion is not true. It implies this is not true. The way I show the proof by contradiction here is very similar to this. Very similar to this. Suppose I say this is a very small illustration. Okay, when n equals to 3, that implies 2n plus 1, maybe just say 2n equals to 6. Now, to prove this by contradiction, you do the following. Suppose n is not equals to 6. Then n cannot be 3. So to prove that this statement, n equals to 3 implies 2n equals to 6, you can show that if it is not this, if this is not true, 2n not equals to 6 implies n is not equals to 3. Now, this is what we call the contraposition. Now, contraposition of a statement is equivalent to contraposition of a statement is always have the same truth value with the original argument. Okay, now notice that the following is not true. This is something totally outside. Okay, we know the following is true. N equals to 3 implies n squared equals to 9, right? Okay. Now, to prove that by contraposition, you basically need to prove that, so that is equivalent to the following statement, that n squared not equals to 9 implies n is not equals to 3. Notice that this is not if and only if. This is not if and only if. The following, the one up here, it is still if and only if. Right? If n equals to 3, then 2n equals to 6. If 2n equals to 6, then n equals 3. Okay? Now, the better illustration is actually the last one here. If n equals to 3, then n squared equals to 9. But if n squared not equals to 9, then n cannot be 3. Now, what it has to do with if and only if thingy? Notice that I cannot say the following, n squared equals to 9. It is not true that n equals to 3, is it right? That's not true. If n squared equals to 9, what will n be? Then n can be negative 3, right? N can be negative 3. Okay, n can be negative 3. But if n equals to 3, then n squared equals to 9, and you don't have n squared equals to 9, then for sure n is not 3. Okay, that's what we say proof by contradiction. I have one case, one of my professor actually showed this logic using a video. So you didn't take any course with proofing, so it's not easy to explain this while you are not taking this that proofing course formally. But my professor once showed this video. Okay, so let's say Thomas is accused of, let's say, murdering Tim. Okay, and his question is how to prove Tom is not the murderer. Okay, so he showed us that basically that video clip, and it shows up the court situation in court, and then my defendant says that I have a witness that will basically show that my client is not guilty. And his witness is Tim himself. Okay, so imagine you are in a court, Thomas is here, okay? And while everybody accused Thomas as the killer, suddenly Tim shows up. Then all the accusation fails, right? Just falls right away. Why? Because you accuse me of killing somebody that's still alive. Does it make sense? So the argument basically is the following: Tom killed Tim. That's why Tim is dead. Okay, now that is equivalent to the statement that Tim is not dead implies Tom did not kill Tim. Okay, now I'm sorry that I used this kind of illustration like killing, murdering something, but this was the illustration we were shown in my class at that time when I was in Indonesia doing my undergrad. You see what I mean? Okay, and the accusation that Thomas killed someone, it's a very, very heavy accusation, right? Somebody accused you of being a murderer. And how do you defend yourself in that situation? If no witness, nobody else, only you and Tim there at that place. Okay, of course, there are other ways to prove that Thomas is not a murderer, right? Okay, but the very definite proof, evidence, is when you can show Tim himself is not dead. So you cannot say Tom, you cannot say I kill him. Why? He's still alive. How can you say I kill him? Does it make sense? Okay, so you see that this statement here, the technique of proving later on, this statement, one way to prove that this statement is true is to show this statement. If you say Thomas killed Tim and therefore Tim dead, then it is also the same to say Tim is not dead, imply Tom didn't kill him. Okay, that's proof by contradiction. Too bad that our time's up. I would like to do more with number 83 actually, but that's actually what you do. Okay, number 84, it's proof by counterexample that it is not necessarily true. Okay, suggested homework from here. Let me do it from your suggested homework. From 11.2, I would like you to do from number 15. Oh, actually, I did a lot of odd numbers already, huh? Do even numbers then. So start from 16 to number 62. Okay, now don't forget that this Saturday, 8 o'clock, we will have a review for test 2, which is only up to 11.1. Okay, only up to 11.1. Of course, this Wednesday we still meet, right? But on Saturday, if possible, set aside some time to meet me for test 3 review. Okay, that's for today. See you then on Wednesday.